Welcome to Brain Vision.
Problem 11.79. We have a garage door that has these wheels that it rolls on a track, but the wheels have rusted so that they cannot roll. So they have to slip, and the kinetic friction coefficient is 0.52. The door weighs 950 newtons. And so the first thing we'd like to find is if this, and it's being pushed to the left at a constant speed by some force. So if this distance h is 1.6 meters, we want to find the y component of the force on each wheel, or that is to say, the normal forces. So we want to use our equilibrium conditions. And this isn't accelerating because the speed is constant, so it's a dynamic equilibrium, but still an equilibrium. So all of the forces and torques still have to add up to 0. So the normal forces on A and B have to add up to be equal to the weight of the door. The horizontal components of the forces add up to be 0 because it's not accelerating. And so then this is the force of friction on A plus the force of friction on B. Have to be equal to the force that's being applied. So W equals NA plus NB, and F equals FA plus FB, little f's for friction. So now FA we know has to be equal to the coefficient of friction times the normal force. And similarly for B. So this lets us find the force being applied is the coefficient of friction times the sum of the normal forces. And we know that the sum of the normal forces is the weight. And so putting in our numbers there, we get 494 newtons. Now, we want to use the torque equilibrium condition. We're going to so we're going to compute torques about point B. So the normal force at B and the friction force at B are both a distance of 0 away from B, and so they have no contribution to the torque. And the force of friction at A is anti-parallel to the displacement vector from B to A, so that also adds no torque. So torques having to add up to 0 gives us the weight times 1 meter, because the weight acts at the center of mass. It's directly between these two. The distance between these two is 2 meters. So this distance is 1 meter. The normal force at A acts 2 meters away. And then minus F times H. So that's the other force that can produce a torque here. So, solving this for NA, we get 80 newtons. And now we know that NA is plus NB equals W, so NB is going to be the weight minus this 80 newtons. So NB is going to equal 870 newtons. So roller B is getting a lot more force than roller A. Which makes sense because this force is sort of trying to rotate the door this way, and so this has to provide a larger force to work against that, because it's sort of being pressed down more here than it is over here. So for part B, we want to find the maximum value of H that we can have before one or the other of these leaves the track. It would be A that'll leave the track, because again it's trying to rotate it this way. So this will lift off, pivoting about this point. So in this case, NA and FA will be 0 because the wheel A is about to leave the track. And so all of the equations we did in the first part are still applicable. NA plus NB equal to the weight. This, we just said, is 0. So the normal force at B is the weight. All of the weight is being supported there. The kinetic friction at B has to be the coefficient of friction times the normal force. And so this is equal to 494 newtons, which is equal to the force that is being applied. And that has to happen in order for the door not to be accelerating. So everything is adding up so far. And we then have the weight times its 1 meter moment arm minus NA, which is 0, minus F times H is 0. So this implies that H is W is W times 1 meter divided by F, which is still 494 newtons. And so this is 1.92 meters. So if you tried to push the door at any distance greater than 1.92 meters from the track, the roller on the left is going to lift off, and you probably would rather that not happen.